Hi, everyone, and thanks for inviting me. It's a pleasure to talk about science rather than worry about coronavirus. So, talk about inflammation and fibrosis, work with Miri Laviv is actually here in the meeting too, and presenting a poster. And this is Miri, and Stefan Kallenberger, who's a MD and a physicist from Heidelberg, and Ruslan Medjitov is at Yale. So fibrosis is I'm just going to close the door here. Fibrosis is one of those problems that cuts across physiology and medicine. And there are a lot of diseases that have to do with excessive fibrosis. You can think of it like a scar, too much scarring, pulmonary fibrosis and pancreatic fibrosis, etc., and liver cirrhosis, as we've heard. And the question is, are there principles we can imagine across tissues? Of course, inflammation is very across tissues. And that's where we could try to use a modeling approach. And there's kind of a sequence where there's an injury, and then there's inflammation, calls in the immune cells, and that's superb for healing. But sometimes inflammation, especially if it exceeds a critical time window, could lead to fibrosis. So a lot of times doctors try to stop inflammation by different ways in order to avoid fibrosis in this classic sequence. And the field of inflammation and fibrosis is extremely complex with all kinds of macrophage states, etc. We try to do the opposite, which is try to find a model that captures some essentials that can guide experiments. And so the framework is that when you have damage, cells in the tissue secrete factors that cause fibroblasts to become myofibroblasts, and also signals that cause monocytes to go in, and the blood vessels kind of open up and dilate, and the macrophages go in. Myofibroblasts kind of try to pull their myo like muscle. They try to contract the wound and also lay down extracellular matrix. And macrophages and fibroblasts communicate with each other. This has become increasingly important awareness, and we're going to talk about this circuit of interactions. And this process can resolve in regeneration. That's to say, the myofibroblasts go away, they die, the macrophages die, the ECM, the scar tissue is removed, and tissues regenerate. I should say there's always also cellular senescence involved before regeneration. That's also important. But it can go another way. It could become a long-lasting scar with too much extracellular matrix and a scar tissue that reduces tissue function. So how can one system lead to these two outcomes, especially if inflammation takes a long time? So as I said, if this is injury and this is time, if you resolve inflammation in a critical window of a few days, you get fibrosis. But if you go beyond it, sometimes it's thought to be like an irreversible process. You get fibrosis. Fibrosis takes months to mature, the scar, but after a few days, it's as if the system makes a decision to go into fibrosis in some medical situations. So what's going on here? And so we study inflammation and fibrosis using a cell circuit approach. And this is, of course, imagining that the cells are in a mixed bag, like Liat said. Maybe spatial features will be extremely important, but we're going to ignore them for now. And we know the circuit based on in vitro work done by Ruslan Medjitov, in which with co-cultures of fibroblasts and macrophages. And in this in vitro work, you could really understand what are the growth factors the cells send to each other and to themselves. And it turns out that in vitro, at least, fibroblasts send a growth factor to macrophages, and macrophages send a growth factor to fibroblasts. And fibroblasts also send a growth factor to themselves. So there's an autocrine loop. And fibroblasts hit a carrying capacity, and the whole circuit kind of stabilizes because of this carrying capacity, and then macrophages are kept at a homeostatic concentration because of this growth factor loop. So when you analyze this, you draw these powerful plots called phase portraits. And on the x-axis is fibroblasts, on the y-axis is macrophages. So imagine that the tissue state is simply the number of macrophages and fibroblasts. And this system has several possibilities. If you have just a few macrophages and fibroblasts, they can't support each other, and they basically go up and then down, and you get a healing situation. Fibroblasts on their own can support themselves because of the autocrine loop and make a scar just on their own. We call that cold fibrosis, kind of an analogy to cold tumors. There's no macrophages in them. But if you have enough macrophages and fibroblasts, there's another steady state called hot fibrosis where they support each other with this autocrine loop. It's a living tissue. Fibroblast macrophages support each other. And this is what we call this state, hot fibrosis. So these are names we invented, hot fibrosis and cold fibrosis, which means fibrosis with macrophages or without macrophages. And there's this bit separatrix, which separates the two cases. If you're below this line here, in the gray region, you go to 0 myofibroblasts and macrophages healing. If you're above this line, you go to hot fibrosis or cold fibrosis. I just want to say that in vitro work, you can actually get a face portrait like that in vitro. So here what you do is you, can you hear me still? Is that you grow fibroblasts and macrophages in different concentrations and follow each arrow is what happens to them after a few days. And that's actually getting those, it's like getting the solution to the differential equation, but from an experiment. So this is a model, and this is the experiment, and you can see these fixed points where fibroblasts on their own support themselves at high levels, but they crash at low levels. And the separatrix, where if you're below the separatrix, you crash, and above the separatrix, you flow to a fixed point. And that's a way in vitro to kind of characterize the cell circuit, and that's why we like this. And that was published in this paper down there. So this model predicts that a transient injury, so what's an injury? You start, after injury, what happens is you get inflammation, right? Inflammation means blood vessels open up, macrophages flow in, rise. But if this injury, this flow of macrophages is transient, the influx stops, and then if you're below the separatrix, fibroblasts, okay, so macrophages support fibroblasts, and fibroblasts start going, but there are not enough of them to support each other. And after a while, the macrophages, the monocyte-derived macrophages and the myofibroblasts disappear, and you have healing. You have no more macrophages. And extracellular matrix rises, that's a scar, and then goes down. And here's the data from Shalev's lab, where looking at different time points in a mouse liver injury model, where you can see monocytes go up and then go down. And this is a situation with healing. You can see this loop very simply, experimentally. Different time points, you just count the monocytes and macrophages. But a prolonged injury, you have more influx of macrophages, more and more, let's say 3 days here, and they cross the separatrix. So there's so many macrophages now, and also fibroblasts are growing, that even if you stop the influx from blood vessels, they can support each other. So macrophages crash and then recover. They crash and then recover, and you're in hot fibrosis forever because they support each other. You don't need any more influx. And that's how a difference between a 2-day and a 3-day injury could be so dramatic, because you cross the separatrix, and then you're also repeating injury. So repetitive injury is known to lead to fibrosis. Here you have an injury that would lead to healing, but then at this time point, another little injury, and you cross the separatrix, and the game's over. You're going to go into hot fibrosis. And you can model the ECM because the fibroblasts make the ECM, but macrophages degrade the ECM. And so there's an interesting game where the healing state has low, very low ECM. The colors here are ECM. The hot fibrosis state has macrophages which degrade the ECM. So it has intermediate scarring, but the cold fibrosis is the worst. It has no macrophages, so you have massive, hard, undigested ECM. So that's a prediction for those of you that want to take a look at fibrosis situations. Take a look, are there macrophages around, and see, do you have hot fibrosis and cold fibrosis situations? And the circuit is bistable. That's why a brief time window leads to healing and a long time window leads to fibrosis. And this can explain puzzling observations in the field. So there's a whole line of work asking what happens if you remove macrophages, because we all want to heal fibrosis. So what happens if you remove macrophages? And sometimes when you remove macrophages, it's good. You get pro-healing. But other times, you remove macrophages, it's bad, and you get bad fibrosis. And this explains it. It's basically, the difference is, if you remove macrophages while there's just a few fibroblasts around, you go to the healing state. But if you're across this point where fibroblasts can support themselves, if you remove macrophages, your fibroblasts support themselves with their autocrine loop, and you get to terrible cold fibrosis. That's why it's so sensitive. It's a paradoxical, what's called a paradoxical effect of removing macrophages. You can understand using this bistability. You can also understand why is it that scar maturation takes months, whereas all this inflammation takes days. So, and the model shows this, and it's basically because when you cross the separatrix, it's crossing like it's like going from it's like a ball rolling up a hill, and then it can go down or it can go above the hill. And this point up here, close to an unstable fixed point, is very slow. And that leads you to, even though turnover time is days, it takes months to actually mature. And you can understand that based on this model. Even healing takes a couple of weeks because of this slowing down next to a critical point. And then you can use the model to ask, how can I prevent fibrosis? I mean, it used to be in medicine that fibrosis is irreversible and oblique, but that's been starting to change because situations, for example, in liver, there was a kind of a pioneering observations. There's a situation that causes fibrosis. That's hepatitis virus C. How's it called? Shalev, this. I'm blanking out on the name of the virus. Yeah. Is that right?
Yes, hepatitis C.
Yeah. So the body can't get rid of this virus, so it encapsulates it in fibrosis. And eventually your whole liver becomes like a piece of dead tire or something like that, and you lose liver function. You can die from this. In the last decade, there's drugs that weren't available before that can remove the virus completely. And then doctors did something unusual. Once the person is healed, they don't want to see you. But if they look for fibrosis a few months after the virus is removed, they saw that the fibrosis also went away. And that suggests that even in humans, serious fibrosis in some cases can go away. So how can we reverse fibrosis? Of course, some diseases like pulmonary fibrosis, idiopathic, you want to remove fibrosis because otherwise or heart failure, which is increasing fibrosis in the heart. So how can you remove? So this model suggests some targets, and one of the attractive targets is this autocrine loop. The fibroblasts secrete a growth factor like PDGF that makes them proliferate. And it turns out that if you remove this autocrine loop, not remove, but weaken it, you change the separatrix. So you increase the gray region, which is the healing attraction. So a 6-day injury, which would make you go to the cold to the hot fibrosis state, now if you reduce the autocrine loop, is now within the basin of attraction. You can even imagine first depleting macrophages a little bit, and then weakening the autocrine loop as a strategy to weaken reverse fibrosis. And when just to make it memorable, I want to sing a song about inflammation. And this song is called When I Find Myself in Times of Swelling, redness, heat, and pain, there will be an answer, inflammation again. And though it may be itchy, it's just my body trying to repair. There will be an answer, inflammation again. Inflammation again, inflammation again. There will be an answer, inflammation again. And when inflammation's over, there's a little scar that shines on me. Shine until tomorrow, let it be. But if I can just reduce that autocrine loop, maybe I'll be fibrosis free. Shine until tomorrow, let it be. Fibrosis free, let me be fibrosis free. Shine until tomorrow, let me be fibrosis free. So, to summarize, I talked about a circuit between macrophages and fibroblasts. Of course, it's a drastic simplification, but it's enough to start to do experiments, as I'll mention, is for some concepts that show you that there's a possibility for hot fibrosis with macrophages, cold fibrosis, which is tougher, more ECM, without macrophages. This could be in dermatology, it could be what's called keloid scars, hot fibrosis, versus like late stage scars called cold, which are like cold fibrosis. Also, heart attacks could be like hot fibrosis versus cardiac failure, which could be like cold fibrosis. And there's a basin of attraction. And you can prevent fibrosis in the model by different measures, for example, reducing the autocrine loop or increasing endocytosis of that growth factor, or slowing macrophage proliferation, or increasing macrophage removal. And I just want to say that it's not like you have to set the autocrine loop to 0. You just have to cross the separatrix, which is hopeful. For instance, you might need to just reduce it by a factor of 2 in order to cross the threshold. It's just like in COVID, you just need to get the replication number below 1, right? Not to 0. Never heard. So it's a more hopeful kind of model. And I want to acknowledge Miri, Stefan, and Ruslan. And now we're trying to experimentally test this in 2 different systems. One is Shoval Me'ar, a PhD student with Elad Sachol, doing experiments on mouse heart fibrosis after heart attacks or cardiac or chronic fibrosis kind of situations. And we're trying to look for hot fibrosis, cold fibrosis, and also in human slides. And with Ruth Shoval, trying to apply this idea to the cancer microenvironment, which also has macrophages and different kinds of cancer-associated macrophages. And during this in vitro study of macrophages and fibroblasts, Tomer Milot and Shimrit Meyer are the graduate students doing this experiment. So it definitely, for me as a theorist, this concept was strong enough to actually start experiments. And that's I think, the only thing you can ask for a theory. It doesn't make you do new experiments. All right, so thanks very much.
Thanks, Ari, for the fantastic talk and for the song. The most popular trending question right now is whether or not your song is available on Spotify, and if not, when it will be.
That's talked with my agent. Shalil is my agent.
I can see how this works, and I can see how you're funding your science. One of the questions that came up is it was really having to do with fibroblasts and macrophage heterogeneity. Barbara said, "Great talk. From my understanding, fibroblasts and macrophages are heterogeneous and can exist in different cell states and different tissues. How are you thinking about modeling that into some of the phase diagrams that you showed today?" Yeah.
So the question is, macrophages and fibroblasts are heterogeneous, and they're probably continuum of cell states, as we see in these single cell studies. And there's spatial aspects. Maybe there's like in Livestock compartmentalized versus mixed. Also in fibrosis. And so my approach as a theorist is to adapt the model to the level of my ignorance. So at this point, I try to make this, I think it's useful to have a whole continuum of models, like from the very minimal to the very complete, and try to see what insights each step gives you and see when it's interesting enough to do experiments. So I could add more cell states and see how each cell state interacts with other ones. And the question is, at what point do I gain a new insight from that? So we definitely want to do that as the next step.
Very cool.
Okay. Thanks, Uri, for this super stimulating and relaxing talk. There's a nice question here from Jessica Whitehead. Any evidence that cells can remember having gone through the process, even if they initially healed without fibrosis, so that later injury responses are somewhat calculated in terms of the previous experiences of the cells?
So let's see if I understand the question. Is there a memory, like once you have a healing, does the tissue remember that? Do I understand correctly?
Some epigenetic imprinting or some kind of cellular memory. So that the second response.
I have no idea. I mean, maybe somebody else in the audience knows and can chip in. I mean, it would be very useful, because then you have like an area which you get abraded off and maybe becomes tougher. I guess, like say, for instance, you can imagine the skin gets thicker. There's a circuit like that where immunoneurostimulation makes the skin thicker, and a malfunction and that causes disease like psoriasis. So there are barrier tissue memory, kind of, you can say. But I don't know, maybe other people can answer it. I never thought about that.
I mean, it's a great question to think about how you might dynamically update the phase diagrams based upon previous experience. Related to that, Hamaria asks, in addition to, Lawton, you're saying, if you thought that the circuit was representative of in vivo, and if there are other cells that you thought you had to fold in to think about the stability of the phase diagram. So obviously there's a close coupling between macrophages and fibroblasts, but what are the other communication partners that might be important in dictating fibrosis?
So what other communication partners? So first, the most important one is the parenchymal cells, like the epithelial cells or something like that, because they get damaged, they instruct them the first signal, then they need to be regenerated. And another compartment, I would say, is senescent cells. So you have senescent fibroblasts and senescent epithelial cells. They get formed within a few days. They send out these SASP, senescent associated secretion profile, that's very effective in doing two things, calling in immune cells and slowing down regeneration. So they're like a plug. So after injury, the cells don't commit apoptosis, but then you have a hole. They go into senescence, which keeps the tissue intact and also its function intact, and calls in immune cells like NK cells to remove them, and stops regeneration. And only after they're removed, there's regeneration. So that, I think, is really an interesting. And like in liver regeneration and heart regeneration, you don't get regeneration without massive senescence before that, a transient. So, like I would say heart regeneration, I mean in P1 mice, for example, we flip the heart, you get massive senescence and then regeneration. And if you disrupt that senescence, you disrupt regeneration too. So that's really an amazing compartment. And that, of course, they can include NK cells and maybe T cells that remove the senescent cells. And it maybe endothelial cells will be important too, right? I guess this model is like maybe a way to establish a little paradigm for two-cell circuit, and then maybe we can have these neighborhoods where we have several neighborhoods. By the way, the diffusion and endocytosis of signals creates a natural range of 100 microns or so, which is the range where you make a molecule until it's endocytosed by its receiving cell. And that creates a neighborhood scale for, let's say, Liat's neighborhoods. And maybe that's a scale where we need a little circuit diagram for each one of those typical neighborhoods. I hope I answered the question.
You did. I'm just going to ask one quick selfish follow-up on that. I was wondering, as you think about fibrosis and obviously the laying down of ECM, you're getting changes in these length scales. How do you think about looking at alterations in the distance for which cells can communicate with one another in sort of this process? Because obviously it's not a static ecosystem. And so I'm trying to think about how you might, add some of that into these models and whether you think it's, nice to model, but not needed to model.
Yeah. So spatial aspects will definitely make a difference. But I want to say one neat thing that we think about, which is that cell communication is a really cool way to adjust itself to how far the receiver is. And that is because most of these signaling molecules are not removed by degradation. They're removed by endocytosis. As I say, they bind the receptor, and only then they get in, and they're just in vivo. That's the main way. And then what that means is that the range scales. If you have very many receiver cells, you quickly lose that molecule. If you have very few receiver cells, the molecule goes until it finds its receiver. So its range is actually scaling with the density of receiver. I hope I explained myself. And that is potentially a way to make to make the circuit invariant to the actual distances. You just need the identity. But of course, there will be spatial aspects that are critical. So that's what I can say right now. I hope it was relevant.
Yeah, very cool.
Great. There's another question here from Jacob El Corte. Great talk. How do you think these circuits are tweaked or evolved during development to achieve different stable tissue states? And if I may add, do you think these phase spaces also change with aging?
Yeah. So the first question is different cell types. So with Ruth Cheval, we're looking at in vitro fibroblasts derived from different cell types as well as cancer microenvironment, and it looks like there will be differences in the phase. So you can actually in vitro measure like where those fixed points are. Some fixed points may go. It looks like different tissues might be different circuits, for at least for the homeostatic component. And aging, yeah. So aging, we think a lot about aging. So with aging, the risk of fibrosis increases exponentially with age. The risk of fibrotic diseases increases exponentially with age. The risk of dying increases exponentially with age. So we have models to explain that, and our favorite hypothesis is actually senescent cells, the same cells that help you so much in regeneration and injury when you're young. When you're old, the way we think about it is there's the source that makes senescent cells accumulate all over, and that source is your stem cells that last forever. They're in you. When they get mutated, and they get about 1,000 mutations per stem cell when you're old, they're going to hit a protein that's going to be damaged in the differentiated cells. And so if you have a mutant stem cell, it's going to make damaged cells. And that means you have an injury right there, here. And the rate of that mutations accumulate is linear with age, because stem cells turnover at a constant rate more or less during adulthood. So with adulthood, you have like as if there's an injury here, because the stem cells are making a column of damage in senescent cells. And that means at a certain age, senescence, which is so useful after injury, becomes the terrible detriment. You have chronic inflammation and you have reduced regeneration all over your body. And that, we modeled that in the paper with Miri. What that does is actually, in many different ways, increase the probability for an injury to go across the separatrix. It moves the separatrix, it boosts the inflammation, and that means that, and that's enough, that change in the probability of an injury to go into fibrosis, the way it changes with age, is enough for us to explain why risk of fibrosis rises exponentially with age. So I think that aging profoundly affects the face portrait, and I think that one of the main players here is the accumulation of senescent cells across the aging organism, and you can model what that will do. So
thanks, Suri. That's awesome.